Hi everyone. In today's video, we will learn how to perform and interpret the two-way chi-square test in SPSS. As a reminder from Monday's class, the two-way chi-square test is similar to a one-way chi-square test in that both tests use categorical variables and involve comparing percentages. However, for a one-way chi-square test, we recruit one sample of people and we compare the observed percentages in that sample against the expected percentages, which are some numbers that we came up with in advance. In a two-way chi-square test, however, we have two samples of people, and we want to compare the percentages in one sample against the percentages in the other sample. So for example, if we know ahead of time that 6% of Americans don't know how to ride a bike, and we want to compare our sample against that number, we could use a one-way chi-square test to see if the percentage of people in our sample who can't ride a bike is larger, less than, or no different from 6%. If, however, we wanted to compare men and women in terms of their ability to ride a bike, we would have to recruit two samples, one of men, one of women. We would calculate the percentage of men who know how to ride a bike, the percentage of women who know how to ride a bike, and then we could perform a two-way chi-square test to see if those percentages are different from each other. In other words, are men more likely, equally likely, or less likely to know how to ride a bike compared to women? In this video, we're first going to work through an example that involved these infant simulators. Some or many of you may have had to care for one of these when you were in high school. Here is more information about how these infant simulators work. As you can see, they are extremely realistic. I would encourage you, if you have the time and interest, to watch this YouTube video that's linked down here at the bottom. It shows you how high school students are asked to care for these babies and how they cry, they need to be fed, and they have computer chips in them so that they can do very sophisticated things like monitor when their diapers are changed, monitor when they've been fed, monitor how they're being held, and so on. Now, again, I'm guessing many of you have done this, and if we were all in the same room right now, I would ask some of you to share your experience having taken care of one of these babies. In my experience, most people did not find this to be a particularly enjoyable experience when they were in high school, but that's kind of the point, right? The point is to show high schoolers how difficult it is to take care of a young child so that they'll be safe and not have an actual young child of their own. The question is, do these infant simulators actually work as intended? Do they actually scare high school students into being safe and therefore decrease the risk of teen pregnancy? To test that hypothesis, a team of researchers in Western Australia recruited a very large sample, 2,834 women who were currently high school freshmen or sophomores. And each of those women was randomly assigned to one of two groups. 1,267 of those girls were assigned to take care of one of these infant simulators. The other girls, 1,567 of them, did not take care of these infant simulators. Now, if they work as expected, what we should see is that the girls who did take care of an infant simulator were less likely to become pregnant before age 19. In other words, less likely to experience a teen pregnancy. So that was the outcome in this study. After these girls participated in the study, they either did or didn't take care of the simulator. They were followed until age 18, and each girl was coded as either a yes or no in terms of whether they did or did not become pregnant before their 19th birthday. The independent variable in this study is therefore whether or not they took care of the simulator. Some girls did, some girls did not. The dependent variable was whether they became pregnant before their 19th birthday. And as we'll see, some girls did and some girls did not. To do this test in SPSS, we're going to use the data file called robotbaby.sav. And as you can see in the screenshot here, for each girl who participated in the study, we know two things. Did they take care of a simulator? Yes or no? And did they become pregnant before their 19th birthday? I'm sorry, their 20th birthday? Yes or no? Our null hypothesis would be that there is no difference between these two groups of girls. In other words, the percentage of girls in the simulator group who became pregnant was no different from the percentage of girls in the non-simulator group who became pregnant. But if these robot babies work as intended, what we should see is that girls who did take care of a simulator were significantly less likely to get pregnant before age 20. To compare the percentage of pregnancies between the simulator and non-simulator groups, we're going to perform a two-way chi-square test in SPSS, and depicted on the screen right now is how we do that. We go to Analyze Descriptive Statistics, which is a menu we've been into before, but we're going to select a new option called Crosstabs. And as we'll see, what we're going to end up with is a table that looks very much like the tables that we saw in the slides on Monday. When you click the Crosstabs button, you will have a list of all of your variables on the left-hand side of the screen, and you will have empty boxes on the right-hand screen that are labeled rows and columns. Your independent variable, which in this case is whether each girl did or did not take care of the simulator, goes in the rows box. Always put the independent variable in the rows box. The dependent variable, which in this case is whether the girl became pregnant or did not become pregnant before their 20th birthday, that variable goes in the columns box. The dependent variable always goes in the columns box. We're not quite done yet. We have to do some stuff in both the statistics menu and in the cells menu before we can click OK to run the analysis. First, in the statistics menu, we're going to make sure to check the box next to chi-square. If we don't check that box, we won't actually get the results of the two-way chi-square test. So that one's particularly important. In the cells menu, we're going to check the box for row percentages. This will tell us what percentage of girls in each group became pregnant. Those are numbers that we're going to eventually want to include in our final answer. Once we've checked the chi-square box in the statistics menu and the row percentages box in the cells menu, and we have our independent and dependent variables in the correct places, we can click OK to run the analysis. The first table that pops up in our output simply gives us the descriptive statistics for our sample. This looks very similar to the tables that we worked with in class on Monday. So as you can see in that top row, there were a total of 1,567 girls in this study who did not care for an infant simulator. Of those girls, 167 did become pregnant, and 1,400 did not become pregnant. Below those numbers, we have the percentages. So if we were to divide 167 divided by 1,567, we would see that 10.7% of the girls who did not take care of a simulator did become pregnant before their 20th birthday. In the second row, we have our other group of girls, 1,267 girls who did take care of an infant simulator. Out of those girls, 210 did become pregnant, 1,057 did not become pregnant. In other words, 16.6% of the girls who did take care of a simulator did become pregnant before age 20. Now, looking at those two percentages, they not only look different, but they look different in the opposite direction of what we might have expected. It looks like the girls who did take care of a simulator, who got pregnant about 17% of the time, were actually not less, but more likely to get pregnant than the girls who did not take care of a simulator, who only got pregnant about 11% of the time. However, there's nothing in this table that tells us whether that is a statistically significant difference. So we can't yet conclude that these two groups are different until we look at the results of the chi-square test, which are shown in the next table. The first row of this table gives us the results of the chi-square test. Our chi-square statistic is 21.27. Remember to always round this number to 2 decimal places. Because we are again working with a 2x2 table with 2 rows and 2 columns, we have 1 degree of freedom for this analysis. Our p-value here, according to SPSS, is 0.000. However, remember that it is impossible for p to equal 0. When SPSS tells us that p equals 0.000, what that actually means is that p is an extremely small number that, when rounded to 3 decimal places, shows up as 3 zeros. Whenever we see that, in our answer, we will write p is less than 0.001. You should not write p equals 0. Because our p-value is so small, it is much, much smaller than 0.05, we will reject our null hypothesis here. And that allows us to conclude that the percentage of girls between the two groups who got pregnant were, in fact, significantly different from each other. And as it turns out, the results of the study were the opposite of what we expected. The girls who did take care of the infant simulator were actually more likely to get pregnant than the girls who did not. Here's how we would write up the results of our study. Always begin your sentence by naming the test that you ran, and complete the sentence in a grammatically correct fashion explaining the results of what you found. A two-way chi-square test showed that girls who used an infant simulator were more likely to get pregnant in their teens compared to girls who did not care for an infant simulator. At the end of the sentence in red, we have our chi-square statistic from SPSS rounded to 2 decimal places, 21.27. We had the Greek symbol chi with parentheses for the degrees of freedom, which in this case was 1. Our p-value, which SPSS told us was 0.000, we are actually going to write as less than 0.001, because again, we know that p can never truly be equal to 0. In blue, in the middle of the sentence, we have the row percentages for each group, telling us that 16.57% of the girls who did take care of a simulator got pregnant, compared to only 10.66% of the girls who did not use an infant simulator. So in short, it looks like this is actually backfiring. By requiring girls to take care of infant simulators, high schools assume that it will deter them from becoming pregnant before age 20. It appears, however, that that actually has the opposite effect. Maybe because it shows them that they actually enjoy it and or it's not as bad as they expected. So it's possible that while schools assume that it's going to make them more safe, it may actually make them less safe. This is an actual study, and those are the actual results. Here are some excerpts from the published research paper in which the researchers explained their study and its findings. So overall, 13% of girls who participated in this study did get pregnant before age 20. And here is where they report the results of their chi-square analysis, showing that 17% of the simulator group versus only 11% of the non-simulator group became pregnant before age 20. Notice that their chi-square statistic is actually the same as ours, and they wrote out the whole p-value. Whereas we said p is less than 0.001, the actual p-value here was 0.00004. So again, a very small number showing a statistically significant difference. For our next examples, we're going to look at data from a series of studies that formed the basis of a series of advertisements that you might remember from a few years ago. The mouthwash company Listerine put out a series of commercials for what they called the study of bold. And if you're curious to watch one such commercial, it's only 30 seconds long. You can click on the link under that video and see what those ads were all about. In essence, what these advertisements did is they claimed that there were statistically significant differences between people who do use Listerine and people who don't. Specifically, the company claimed that people who use Listerine are more likely to have done certain bold things in their lifetime compared to people who don't use Listerine. Here's a map that summarizes some of their findings. So for example, the company claimed that people who use Listerine in the United States are more likely to have gone skydiving compared to people who don't use Listerine. In Europe, they claimed that people who use Listerine are more likely to have gone running with the bulls compared to people who don't, and etc. for all the rest of these bold, unusual activities. But are people who use Listerine actually more bold than people who don't? We're going to pick out two of these behaviors using the data file listerine.sav to compare the percentage of people who have been in a food fight and the percentage of people who have been to a haunted house between two groups, people who use Listerine and people who don't. Our null hypotheses here would be that people who use Listerine and people who don't use Listerine are equally likely to have been in a food fight and equally likely to have been in a haunted house. Our alternative hypothesis, if indeed Listerine users really are more bold than people who don't use Listerine, would be that the percentage of Listerine users who have been in a food fight is higher than the percentage of non-Listerine users who have been in a food fight, and same for the haunted house. Now, for the first of these analyses, as a reminder, we would go to Analyze Descriptive Statistics crosstabs. We would put the Listerine variable in the rows column because that would be our independent variable here. And for our first example, we would put the food fight variable in the columns box as our dependent variable. In the statistics menu, we'll make sure to check the box for chi-square so that we can get the results of the chi-square test, comparing Listerine users against non-Listerine users. And in the cells menu, we check the row percentages box so that we can find out what percentage of Listerine users have been in a food fight and what percentage of non-Listerine users have been in a food fight. On this slide, I show you the output from that chi-square test, and I encourage you to try recreating this on your own to make sure you get the same numbers. Before I interpret this output, I'm going to show you a few questions on the screen, and I encourage you to pause this video and try to answer these questions on your own before I give you the answers. So first, how many total Listerine users were in this study? Second, what percentage of Listerine users have been in a food fight before? Third, what percentage of non-Listerine users have been in a food fight before? And lastly, and most importantly, is that a significant difference? Are those two groups of people different in terms of the percentage of people in each group who have been in a food fight? If you would like, please pause your video now, take a moment to answer these questions, and then we'll go over them together. All right, let's now practice reading SPSS output by going through the answers to these questions together. First, there were a total of 1,500 participants in this study, 767 of whom do use Listerine, 733 of whom do not. So the answer to our first question is that there were a total of 767 Listerine users in this study. Of those 767 Listerine users, 83 said that they had been in a food fight. 83 divided by 767 gives us 10.8%, which is the answer to our second question. In our sample, 10.8% of Listerine users have been in a food fight. In our other group, that percentage was only 8.2%, or 60 people out of 733. Looking at those two numbers does not tell us if they are significantly different. In order to find that out, we have to look at the results of our Pearson chi-square test in the bottom table. Our chi-square value for this study is 3.02 with 1 degree of freedom, and our p-value is 0.082. Because 0.082 is larger than our alpha value of 0.05, we would retain the null hypothesis here and conclude that there is not a statistically significant difference between Listerine users and non-Listerine users in terms of the percentage that have been in a food fight. In other words, 10.8% of Listerine users have been in a food fight, 8.2% of non-Listerine users have been in a food fight, and the results of our chi-square test tell us that that is not a statistically significant difference. If I were to ask you to write up the results of this test, your answer would look something like this. A two-way chi-square test revealed that people who use Listerine and people who don't use Listerine were equally likely to have been in a food fight, with all of those numbers coming from the output on the previous slide. For practice, here is our second practice problem with the study of bold Listerine dataset. Here we are looking to see if Listerine users and non-Listerine users differ in terms of whether they've been to a haunted house before. So we have two groups of people, again, Listerine users and non-Listerine users. And for each person, we know if they have or have not ever visited a haunted house. Using the output from this analysis, pause the video and try to write up your answer in proper APA format. Is there a significant difference here? Okay, let's look at our output. In the top table, we see that 81 out of the 767 Listerine users in this study have been to a haunted house before, which comes out to 10.6%. Only 41 of the 733 non-Listerine users in this study, or 5.6%, have been to a haunted house before. Therefore, just by comparing those two percentages, it looks like Listerine users are about twice as likely to have been to a haunted house compared to non-Listerine users. However, we still don't know if that's a statistically significant difference until we look at the results of the Pearson chi-square test in the bottom table. For this study, our Pearson chi-square statistic would round to 12.38 with 1 degree of freedom, and our p-value is extremely small. Because SPSS says that p equals 0.000, we know that in this case p is less than 0.001 and certainly less than 0.05, indicating that there is a significant difference between these two groups. It looks like Listerine users are in fact more likely to have been to a haunted house compared to non-Listerine users. And if we want to write up the results of our analysis, here's how it would look. A two-way chi-square test revealed that people who use Listerine were more likely to have been to a haunted house compared to people who don't use Listerine. And again, we get the row percentages from the previous slide, which are shown here in blue. We also get the results of our chi-square test with the chi-square statistic rounded to 2 decimal places, and our p-value written in this case as p is less than 0.001. Lastly, another way for you to practice performing two-way chi-square tests would be to play around with the data from the class survey that you filled out at the beginning of the semester. Remember that two-way chi-square tests are used to test for relationships between two categorical variables. So you could look at the list of questions from the class survey, pick out two categorical variables that you think might be related to each other, and run a two-way chi-square test to see if they are in fact related. For example, there probably is a relationship between housing and pet. In other words, people who live on campus are maybe less likely to own a pet compared to people who live off campus if there are restrictions about owning a pet if you live on campus. There may also be a relationship between sex and speeding. Perhaps it's the case that men are more likely to have gotten a speeding ticket compared to women. Because both of those variables are categorical, we could test that hypothesis using a two-way chi-square test. So as you're practicing running this test in SPSS, what I would recommend is getting together with a classmate, coming up with a series of hypotheses that look for relationships between two categorical variables. You each independently run a two-way chi-square test to see if those variables are in fact related, write out your answers, and then compare them with each other to make sure that you got the same answers, and check each other's work in the process.